I told my morning class. Oh, I interrupted. That was weird. I told my morning class that it felt like I hadn't lectured in a month because we had a study day and then we pushed the test back and then we had a holiday. So it feels like it's been a while. Um, there's something else I was going to say. I don't remember what it was now. Oh, the tests are graded. So make sure you go check out your test score. If you have questions, if you want to chat about it, let me know. I also graded all the formal reports. And with your formal reports, I know it's weird. With the formal reports, I did fill out the rubric for everybody. So you will have a PDF that the name of the PDF is your name. And so it's uploaded there. If you emailed me your formal report for whatever reason, then you're going to have two things to look at. There's again both your name. One is a picture folder. It's your lab report just with my notes on it, and then the other one is a oh my it just told me my internet connection is unstable. Let's see. I'm going to do this. All right, give me 1 minute here. I have an Ethernet cable that I can plug in, but it takes a little bit of adjusting and moving. But we'll see if that helps out. Yeah, I noticed because I have my laptop open and it froze on my laptop. So I wasn't sure if that was my laptop acting up, but let's see. Yeah, it told me my internet was unstable, but I plugged in my Ethernet. So hopefully that'll do it. Um, so I'm going to continue to work on grading lab reports, but after you guys turn in the lab that's due today, you're actually not going to be turning in lab reports for a while because we'll start the lab practical today. And that's actually not due until the last day of the semester or last class day of the semester. So I will get lab reports back to you, but I'll just work on them as I have time. I think that's all. Let me get our PowerPoint slides up here. Okay, there we go. Let's do this. Okay, where's my stylus? Here it is. So chapter 21 is alpha carbon chemistry. So what we're focusing on is the carbon that is right next to a carbonyl carbon. And we're going to be looking at aldehydes and ketones as well as carboxylic acids, esters, and other carboxylic acid derivatives. Um, but we're specifically focusing on, oh, did I freeze again? Am I unfrozen? Are we good?
We could see you just fine.
Okay, all right. It froze on like my own laptop in a really strange facial expression. So
I think your Ethernet's working pretty good.
okay, good. Good. I usually have it plugged into my laptop because my laptop is slow and old. But I did just get a brand new one. I got a fancy new gaming laptop, so we'll see how that works. All right, so alpha carbons, we're going to turn them into enols and enolates, which is actually a term we have used before, but it's been a while. We haven't talked about enols and enolates since our alkyne chapter. So here's our little definition type of page. So next to our carbonyl carbon, we have the alpha carbons, and then attached to those are betas, then gammas, deltas, epsilons, and so on as you go down the chain. We give them a name because it's the one we're focusing on. So we've talked about this before. It's just easier to say alpha carbon than it is to say the carbon next to the carbonyl carbon. Oh, I don't know, guys. I will have to figure that out. Really, I just wanted one with a huge screen and a 10 key number pad because it's easier to type in grades. So I will share that with you, but it's not something I know about. What we're going to turn these ketones and aldehydes and whatever other type of carbonyl we're working with into are enols and enolates. And the only difference between the enol and the enolate is whether or not it has a charge. So when we're making an enolate, it can only be done under basic conditions because it's going to have that negative charge. So we know that when we're making something under acidic conditions, it can only have, oh, that's a good question. We'll get there. When we're making something under acidic conditions, it can only have a positive charge or it can be neutral. And so when we're making something under basic conditions, it can be negative or be neutral. So if there's more than one carbonyl group, what we're looking at is the hydrogen that's getting removed. So if a hydrogen's attached to an alpha carbon that makes it an alpha hydrogen. When we remove that alpha hydrogen to make an enol or an enolate, we're going to remove whichever one is the most acidic. So that comes back to ARIO and conjugate base stability. So if it has more resonance, then that's going to be the one that's more acidic. If we're just talking about ketones and aldehydes, then there really might not be a difference, and you might get mixtures of products. On the next slide, we'll look at a very specific type that has two carbonyls, though. And so that we won't look at a whole lot of structures that have more than one carbonyl unless they fall into a specific type of category. And so we'll get a little glimpse of that on the next slide. To make the enol, we can use acid or base. For the base, under the enol conditions, we would have to have like water or just a smaller amount of base, or follow it up with a proton source to make sure that it goes back to being neutral. The word enol is alkene and alcohol. So remember way back when we talked about if you take a triple bond and you react it with acid and water, you make an enol, and then it turns into a ketone. That was one of our reactions that we learned. So a ketone and an enol are isomers of one another, and the word that we use for that, the specific word, is tautomer. So we've talked about a lot of different types of isomers, especially going back to early chapters. Tautomers, well, actually, let me take a step back from that. These are not resonance structures. In resonance, we can only move electrons around, but in this, we are moving a hydrogen around. So they can't quite fall into that resonance category. So tautomers are specifically the two structures in the ketone form and the enol form. And when we're going through that process of switching from one to the other, it's called a tautomerization, which totally sounds like a made up word. Well, I guess it was made up at some point, right? So that is the mechanism type when we go from a keto to an enol, or an enol to a keto, or the enolate. I'm looking at my notes here. I think we talked about all that. When we start to look at the actual reactions in this chapter, notice that the last structure in this little diagram down here has an X added to that alpha carbon. So that's what we're focusing on, is we're turning a ketone into an enol or an enolate because it makes that alpha carbon reactive. So in these two structures, that alpha carbon is now part of a pi bond, and we can use those pi electrons to do a nucleophilic attack on something. So we've gone from having a carbon that isn't reactive, it doesn't have any pi electrons, doesn't have a lone pair, doesn't have any electronegative atoms, to now being reactive because it has that pi bond. Most of the time when we do the reactions, we will be using the enolate form, not all the time, but most of the time, because having that charge there will actually make it even more reactive. The ketone form of these tautomers is usually the favored form. So we do have equilibrium arrows between them. These two, the ketone and the enol, are always in equilibrium with each other. So every time we've drawn a ketone, it is in equilibrium with its enol counterpart. There's a couple exceptions to that rule though. This guy down here, this is called a, well, okay, it has two names. It's called a beta diketone. And so this goes back to Justin's question about, well, what if there's two carbonyls? This is the specific scenario I was mentioning. When we have two carbonyls that are this close to each other, the alpha carbon that's in between them, the hydrogen on that is going to be very acidic, because when we have it as a carbanion, that lone pair can go to the left or the right for resonance, and that makes our conjugate base more stable, which makes the acid more acidic. And so this one has essentially twice as much stability than just a regular alpha carbanion. And so it's going to favor the enol side for that reason, as well as hydrogen bonding. So when we're able to put that hydrogen onto the oxygen of the enol, it can hydrogen bond with the oxygen of the other carbonyl. And look at the shape that they form. They essentially form a six-membered ring. So this wouldn't work if the ketones were right next to each other, or if they were too far away from each other. It wouldn't form that nice, perfect six-membered ring that we already know is really stable. I did say this has two names. The other name is a 1,3 diketone. Oops. Oh, I see that comment over there. Let me go read it. A lot of time notes in chemistry, acids are talked about more and preferred. More of them, or just? You mean like when we compare acid strengths? I'm not sure I understand what your question is, Justin. Acids more than bases. Oh, so nature doesn't really have. No, honestly, I don't know the answer to the nature one. I would think that it's pretty evened out, but I don't honestly know. And why we talk about acids more? That is a good question. Acids actually provide a less stressful environment to most chemicals. They are providing a hydrogen to whatever we're reacting with, as opposed to a base, which would rip a hydrogen away. And so whenever we're reacting things, we do want to use the least invasive chemicals possible, or least invasive conditions. So like we don't want to heat something up really high or use really high pressures if we can avoid it. So that might be why. When we're talking about acid base and acid strength, we we essentially just use one of them, right? So for this, we compare conjugate base stability and use that to kind of reason out everything else. Honestly, that's just the way that our author does it. This whole ARIO thing that our author does, I really love it, but it is just our textbook. You won't see that in another textbook. So that might also kind of go into it just based off of the authors that you've used. The other scenario that's on here where the enol is more favored is our phenol down here. So it looks kind of funny to think that the ketone version over there is the same structure, or a tautomer of the same structure, uh, because we wouldn't ever draw it that way. The phenol is going to be much more favored because it's aromatic. And I'm going to add hydrogen bonding over here. I didn't fill in the actual words. Yeah, so they're actually always in equilibrium. The ketone and the enol are always in equilibrium with each other. It's just like, look at the percentages for the one up above there. If you had a solution of that cyclohexanone, less than 0.01% of it would be in its enol form. So it will have some in that form. It's just a very small amount. So we're going to use some acid or base to kind of help it get into that form. Also, the name phenol here, we have the word enol right in the middle there, but then it starts with a pH. So it's a phenyl group that has an alkene and an alcohol. So we talked kind of about the difference about the pronunciation of phenyl versus phenol. This kind of plays into that, about those functional groups and why we say them in a certain way. Okay, let's talk about how to form these enols. We're going to look at two different ways, because we're going to look at acid and base catalyzation. So we're starting acid. And the steps that we're going to do for the acid versus the base are exactly the same, just in opposite order. So, and really it's just two different proton transfers. So we're starting with a proton transfer. So here's my acid. So we just have hydronium there, just generic acid. We're just going to do a proton transfer onto that carbonyl. And then we have a little bit of resonance here. And so we're just going to take that pi bond and move it up into a lone pair position for that oxygen, which creates a carbocation. And then in that last step, we're going to do one more proton transfer. We're going to use water, and the water is going to remove an alpha hydrogen. So we're going to do a deprotonation of an alpha hydrogen. So it grabs that hydrogen, and then the electrons are going to go to form a double bond between the alpha carbon and the carbonyl carbon. And then we end up with our enol over here. Justin, I know you tried to ask a question or say something, but you definitely still sound like an alien. Very sorry. Just make sure that you're still in alien mode. Did you actually have a question though? I don't want to skip slides if you actually wanted to ask something. What if these reactions take some time because of the water potentially taking the other hydrogen? Oh, taking the hydrogen that's attached to the oxygen is what I'm assuming you mean? Yeah. Yeah. So notice they are all fully equilibrium arrows. So yes, it can take some time. We're going to look at some bases specifically that help push that reaction towards the product to prevent it from being in equilibrium, to prevent it from going in reverse. So yeah, great question. All right, let's look at the base version then. Generals. No, that's a good question. Big picture, yeah, it's good to know. It's important to know. In terms of like filling stuff out on a test for me, I don't care if you know. We talk about reactions going in one direction, so we talk about them just in their forward pathway. So if you don't put in the equilibrium arrows, to me that's okay because we aren't talking about it going in the other direction. But big picture, if you were to actually do these reactions in the lab, you would want to know so that you could figure out ways to control it and manipulate it. Oh, yes, I will mark them. So we will mark, that is a good question, and we will start by marking these two. So these two aren't technically reactions. These are kind of like prerequisites to reactions. So when we look at the rest of our reactions, we have to get to an enol or an enolate, and then we can do the rest of the reaction. So we will actually see these pieces of mechanisms in the rest of our mechanisms again. So yes, I will go through and add stars as we talk about stuff. So this one is our base catalyzed reaction. We're starting with that proton transfer again, but we're going to do the opposite order. Oh, I see your comment question. It's a hard time really punching. Yeah. And we did we do, I can't remember if we did this one. I'm looking in my notes here. Oh yeah, we did do this one under basic conditions. Yeah. So these are labs that don't always get great yields because there's that equilibrium. So we tried to do some things that will help push it forward. But in reality, doing these in person, generally, we're happy with a 50% yield because you have to take into account some loss of product, just transferring and stuff. But then you have to take into account that there's going to be a lot of starting material still remaining. So we're going to do the exact same two steps, just flipping the order. So we're going to start with our base, and we're going to remove that alpha hydrogen and create a carbanion at that alpha position. So again, we have some resonance here, and both of these resonance structures are enolates. So when we start to do reactions, a lot of times we will use the enolate version because it is more reactive. We could technically start with either of these enolates, but most of the time we will use this one that has that carbanion, mostly because it kind of saves us a couple arrows and we can start at that lone pair. And we'll see that in the next few slides as we look at some actual reactions. So the resonance here is we're just taking that lone pair and creating a pi bond, and taking the pi bond and making a lone pair. So just kind of doing a little domino effect there. And then in the last step, we're doing one more proton transfer. So we're putting the hydrogen onto that oxygen to make it neutral. And then we get our enol, our neutral enol, back in the end. So I'm going to do one more mechanism on this slide. So this kind of goes along with the reversibility thing that we were talking about. We do need to know how to do these mechanisms in reverse. So I'm going to start with my enol here. And we're going to turn the enol back into that ketone. So we're going to start by doing that proton transfer. We're going to take that hydrogen off of that oxygen. I did not leave myself a bond there. There we go. And then this is the resonance portion. So switching to the other enolate. So I'm going to take lone pair to pi bond to lone pair. And then our last step would be to use water to protonate that carbanion. Let's see, let's do the brackets there. So we're going to grab that hydrogen. And then we go back to having our neutral ketone. So we can show those exact same steps, just going in the opposite direction. Questions about either of those mechanisms, so the acid or the base tautomerizations? Okay. So this is, again, looking at that enolate form under basic conditions. And how we are going to react it is shown down here. And really, this is showing the same reaction just in two different versions. And this is what I was mentioning on that last slide. So the E with the positive charge is just representing an electrophile. But we're going to take our pi bond there and do a nucleophilic attack on our electrophile, or we can start at the lone pair and do our nucleophilic attack on our electrophile. Really, the only difference is that if we do that first method, we also have to show a lone pair forming a new pi bond to form that carbonyl. For the most part, if you have an enolate because you're in basic conditions, either one of these will work. As I said, if we're under basic conditions, that one's the more common one to see just because it only requires one arrow. But there's really no other reason than that. Let's see, I'm looking at my notes, see if there's anything else. Enolates, talked about that. Okay, yeah. So going again with the idea of reversibility and talking about how to kind of push that reaction forward, this is an acid base reaction. We're using a base to remove that hydrogen off of that alpha carbon. And in order to do that, we have to look at some pKa's. So looking at our pKa's for acetone through our ethanol there, give it its proper name, they're fairly high pKa's. And alcohols have approximately a similar pKa. And so what that means is that if we try to use like ethoxide, negative OET, and we try and use that to remove that hydrogen, we know that what's going to form would be ethanol because it's going to form the conjugate acid of whatever base we use. If ethanol has a similar pKa to that alpha hydrogen, then we're going to have a big mix of the products and the reactants. What we want to use is we want to have something that will push the reaction forward and not have starting material left behind. So using something like an alcohol would just give us that mix of ketones and enolates. Now, in all honesty, we're going to want that sometimes. And actually, we'll see that in our fifth reaction. I'm trying to remember off the top of my head, but we'll see it today before we're done. So here's the two common bases that we're going to use. Sodium hydride, so NaH, and LDA, or lithium diisopropyl amide. So we have three reactions on here. I'm just going to kind of divide them up. So let's look at the first reaction. The first reaction is showing sodium hydride in action. We don't care about the sodium. It's just a positive counter ion. We care about the hydride. We saw hydrides in our last chapter. Lithium aluminum hydride, sodium borohydride. We know that hydride means that it's a hydrogen with a negative charge. So here's our hydride acting as a base. It's grabbing onto that alpha hydrogen. And so we make our enolate, we make our carbanion. That hydrogen and hydrogen make hydrogen gas. Forming gas as a side product or a product that we don't necessarily care about is great because it bubbles away. And so as it's bubbling away, we are quote unquote losing a product or removing a product. Le Chatelier's principle tells us that when we remove a product, it pushes the equilibrium towards that product side to make more of it. So as that bubbles away, it's going to prevent that reversibility, and it's going to prevent the ketone from staying in its ketone form. It's going to push it all to that enolate form. So the other one that's on here is LDA. The middle reaction is showing us how to make LDA. So this is on here because you might see it written this way. So we have diisopropylamine, so a nitrogen with two isopropyl groups attached to it. This guy right here is called butyl lithium. The lithium's just the cation. The butyl has a negative charge, and so it's acting as a base to remove the hydrogen from that amine so that we can make lithium diisopropyl amide. So a nitrogen with two isopropyl groups attached to it. It has a negative charge. Again, that lithium is just there as a cation. So you might see it written on an arrow as diisopropylamine, DIA. And butyl lithium. And then whatever it's reacting with underneath it. So essentially, it's kind of being made in the solution. For our purposes, you can write it as LDA. I just want you to know what that means when you see it. So then the last reaction on here is showing LDA acting as a base. So again, we're doing the same thing. The nitrogen is grabbing onto that alpha hydrogen. We make our enolate, and we make an amine. Now, in the first reaction with the hydride goes away. So we don't even need to compare pKs. We don't need to think about it that way. In this reaction, there's our acid, there's our base, there's our conjugate base, and there's our conjugate acid. And so when we're comparing to say which side the equilibrium is favoring, we're looking at the pKa of our two acids, our acid and our conjugate acid. And our acid that we're starting with, that alpha carbon and alpha hydrogen, has a much lower pKa, so a much stronger acid. And so that's going to be what drives the reaction forward. The conjugate acid that forms is a very, very weak acid. In fact, we would still refer to that as a base because it's a nitrogen with a lone pair. Just in this reaction, it is the result of a base gaining a hydrogen. Remember, though, that pK is a logarithmic scale. So the difference between 16.7 and 36 is a difference of about 19. That That means, though, that our alpha hydrogen is 10 to the 19th times more acidic than the amine is. So it's so much more acidic than we're not even using equilibrium arrows. We're using a regular reaction arrow because it's not going to have any reactant left. So, long story short, these are our two base options when we want to push that ketone or aldehyde fully over into its enolate form. Okay, we are going to look at our first reaction then. Oh, no, we aren't. I lied. Sorry. One more slide. Actually, there's two more slides. I totally looked at the wrong number on my notes. Um, I mentioned the 1,3 diketones or the beta diketones before. Because that hydrogen is more acidic, it has the double resonance, it has the hydrogen bonding to help stabilize it. We can use a weaker base. So we can use an alkoxide or a hydroxide because it is still going to be a stronger acid than the alcohol that forms. So again, there's our diketone, there's our alkoxide, so acid, base, conjugate acid. And when we compare our pKa's now, so a difference of about 7-ish, our beta diketone is still 10 to the 7th times more acidic than the alcohol that forms. And I mentioned this a little bit ago, but we wouldn't want to just throw LDA at this or just use the strongest base just because we have it. Because the stronger bases, the stronger the acid, the higher the temperature, the higher the pressure, can cause other side reactions. It can cause molecules to break apart when we don't want them to, or to break down. So we want to use the least harsh conditions possible. So that's why we talk about this one specifically, and that we can use that weaker base. All right, here's our little summary then of which bases we use in which conditions. So if we want to have only the enolate, we're using sodium hydride or LDA. If we want to have a mixture of the enolate and the ketone, that's when we can use ORs and OHs. And then if we have a beta diketone, no LDA at all, we can just use the ORs and the OHs to get to our enolate form. So a nice little summary. This is totally stolen from your book, but a good little summary to help us remember when and why we would use each of those bases. Okay, now we're going to talk about, is LDA bad too? It's not that it's bad, it's just that it's such a strong base that it's just very, very reactive. So we oftentimes look at some small examples. I mean, essentially every ketone that's on this page is as small as it could possibly be. But if we're dealing with something larger, like if you look at structures for pharmaceuticals, they're very large molecules. So so you want to be able to not look at your structure with blinders on just because you want it to react right here doesn't mean it will. You have to think about what else is it going to do to the rest of the structure. All right, reaction number 1. So our first handful of reactions we're going to look at, 1, 2, 3, 1. I was going to tell you, but now I'm not 100% sure. I think 1, 2, and 3, I guess, are all halogenation reactions. So we are doing an alpha halogenation. So reaction number 1 is looking at the alpha halogenation of a ketone in acidic conditions. So there's our ketone, there's our acid, and there's our halogen. And for this one, we can actually use chlorine, bromine, or iodine as our halogen. We don't see iodine pop up very often, but it can be used in this scenario. Oh, sorry, trying to adjust my other screen. There we go. We do have the mechanism here. We do need to know it. The first part of the mechanism isn't shown though. So as I mentioned when we did our enol and enolate mechanisms, the first part is forming the enol. So I'm going to skip back a couple slides. Right here, this is how we would start that mechanism. We would use our acid to get us into the enol. Then we start right here. So for a lot of our mechanisms we're going to look at, we are starting with an enol or an enolate, depending on if we're in acidic or basic conditions, and then we do the specific reaction. So if this is a test question, though, you would need to show how to get to that enol or enolate. The rest of the mechanism, then, we're starting at that pi bond. We're doing a nucleophilic attack on our halogen. There's a couple other things that are happening at the same time. We're going to form a pi bond between the oxygen and the carbon. So really we're reforming that carbonyl. And then the other halogen has to take off. The other halogen is our leaving group. And then essentially we have our product, but it's a protonated version of our product. So the last step is just a proton transfer to get that extra hydrogen off of our carbonyl. And then we have our alpha halogenated ketone. So really we're just adding a halogen onto that alpha carbon. I mean, it's the name is nice, it makes sense, it works with it. There is some regioselectivity right there. The major product is going to be when the halogen adds to the more substituted side. And it actually doesn't have a whole lot to do with the halogen portion. It has to do with that enol. In the enol, the double bond would form on the more substituted side because we know that a more stable double bond is when it's more substituted. So in that intermediate, we are looking for the highest stability. And in this case, that means the most substituents. Yeah, I think that's all I was going to say. See if there's else on there. We are going to do a practice one with this.
Professor?
Yeah, go ahead.
Could this reaction be used to make reagents for a Frito craft?
Yes, it definitely could. And that's it's a good question that you bring up because this right here actually isn't usually the final step. I'm looking to see if it's where we talk about it in my notes, or if I think I just need to put it on the slide. A very common second step is after you have that alpha halogenation to react it with more base and do an elimination reaction. So make an alpha beta unsaturated ketone. So this doesn't get its own reaction number in our book, in our chapter. But it is a reaction you need to know. It is actually just one of our elimination reactions. But it's an easy reaction to do, like in terms of reaction conditions, because we are making a conjugated double bond, which again is higher in stability. So kind of going off the Friedel-Crafts thing, this is a really good kind of launching point or starting point for a lot of other reactants, not necessarily keeping that halogen at that location. All right, we are going to practice one for this. All right, that is what we're going to start with. We're going to draw out the full mechanism, draw out the full product. I'm going to stop sharing my screen just for a second. I think I have my pen has a little bit of lag to it, and that's usually when I have too much stuff open up. So I'm just trying to close everything I don't need. Okay, I think I'm down to the bare minimum now. Let's try this again. There we go. Okay, so we need to start the mechanism by turning our ketone into an enol. So let's see, I'm just going to redraw this down here.
Professor, when there's just an H3O plus without the brackets, that still shows that it's an acid catalyst?
Yeah, the brackets usually mean that it's under like a catalytic concentration. So usually it means that it's like a small concentration. Because, you know, if you remember back to general chemistry, the brackets meant molarity. And so that's why we kind of include it with something like this. But it still means the same thing, whether the brackets are there or not. It just might mean that when the brackets aren't there, that it's in a higher concentration.
Okay. So what about when it's like one NaOH, two H3O plus? But that's not with this one. I'm just saying, like, I think it was for like an acid chloride, maybe. Is that still also an acid? Is the H3O plus there also an acid catalyst?
It would be a catalyst if the acid gets reformed. So like if we take a hydrogen off of it and turn it into water, if at the end of the reaction it gets the hydrogen back and turns back into H3O plus, then that would be a catalyst. So having a specific concentration doesn't necessarily make it a catalyst or not. It's whether or not it gets reformed by the end of the reaction.
Okay, thank you.
You're welcome. So we're going to start with a proton transfer here. And then we're going to do a little bit of resonance. So we're just going to move those electrons up there. And remember that when we're under acidic conditions, everything either needs to be neutral or positively charged. And when we're under basic conditions, everything either needs to be neutral or negatively charged. So kind of keeping that rule in the back of your head can help you make decisions in terms of should there be two arrows here or one arrow. And if you end up with the wrong charge for the scenario, then that might help you make that decision. All right, last step then, I'm going to draw in my alpha hydrogen here. And so this step right here is what shows us that our acid is a catalyst, because we're going to use water to grab back onto that hydrogen. And when we do that, we're reforming our H3O plus. So this does show us that we made, I'm going to do that we made H3O plus again, but that it was a catalyst.
Professor?
Yeah.
Why is it not taking the hydrogen from the terminal end? Why does it take it from...
So that's a great question. And the reason why is actually because of the enol right here that I just drew. The double bond when we take the hydrogen from the alpha on the right, is going to give us a tetra substituted alkene. If we went to the other side, we would have a di-substituted alkene. Alkenes are more stable when they have more substituents. So on the other side, it would still form, but it would be our minor product.
Okay, thank you.
Yeah, I didn't see your question until right then. All right, so we've made our enol. So now we actually have to do the rest of the reaction, though, with our iodine in this case. So here's my iodine molecule. We're going to do a nucleophilic attack from our pi bond. And then the other iodine is going to leave. So right there was actually an SN2 reaction. We did a nucleophilic attack and loss of a leaving group on that iodine. We do need one more arrow, though. We're going to do an arrow right here so that we can reform that carbonyl bond. So we're going to have an iodine at that alpha position and our methyl. We have our carbonyl. And so right now our carbonyl still has that extra hydrogen attached to it. So we just need to take that off. We're going to use some water to do that. But that gets us our final product. So that's our alpha halogenated ketone. And we've added that halogen to the more substituted side because we made a more substituted alkene in our enol. Questions at all about that guy?
In terms of adding the iodine on the more substituted side, would the iodine even have a choice of going onto the other side with the oxygen forming a double bond?
Wait, say that again. I didn't understand. I'm sorry.
I'm not sure if I even understand myself, but so the iodine adds on to basically the side that isn't the carbonyl. It only has the option of going
Oh,
there.
I see what you're saying. Okay, so when I say other side, our iodine is either going to add there or there.
Oh, okay.
So not the other side of that double bond, but like we would have to make this enol and then it could add to the other alpha carbon.
Okay, that makes sense. Thank you.
You're welcome. So in this case, we did talk about a major and a minor product. There are ways to kind of avoid that. One of them would be to use an aldehyde. That aldehyde is not alpha. It's not an alpha hydrogen. It's obviously not an alpha carbon, but it's not in an alpha position. It's a carbonyl hydrogen or an aldehyde hydrogen. So when we're using an aldehyde, there's only one alpha carbon. And so we often will use aldehydes for examples because they're only going to produce one product. Another way to limit the number of products is if we have one side of our ketone that doesn't have any alpha hydrogens. So a common way to do this is to put a benzene on one of the sides. So that is an alpha hydrogen right there, but it doesn't have any hydrogens. So when we form that pi bond or when we remove an alpha hydrogen, it can't participate. So it forces the reaction to go to the other alpha carbon. So you will see a lot of benzaldehydes in this chapter for that reason. All right, let's look at reaction number 2. So reaction number 2 is actually the same idea, but with a carboxylic acid. You do not need to know the mechanism for this one, but it's an alpha halogenation on a carboxylic acid. This one does have a name, and I think it's one of the best reaction names because it's ridiculous, but it's called the Hell-Volhard-Zelinsky reaction. Because it is so long, it gets abbreviated as just HVZ. But I think it's hilarious because that means there's 3 scientists out there with those 3 last names. So that means at some school, at some point, people were taking a chemistry class from Dr. Hell, which I don't know. That's just great. I think it's hilarious. So for this reaction, we're starting with our carboxylic acid. We're going to react it with Br2, PBr3, and then in a second step, water. So this will add a bromine to our alpha position. And again, this could be followed up with some type of elimination to get that unsaturation step. But right now, we're just looking at it as a halogenation. And then number 3A down here. So you do need to know the mechanism. I think my star there is left over from the morning's class. This is also a alpha halogenation for ketones, but now we're doing basic conditions. So there's our base, and again, a halogen, same group of halogens that we can be that we're using the same group of halogens that we saw on our first reaction. This little bullet point right here says that it can be difficult to stop it at the monobromination. So meaning it will add more bromines than we want it to. So for reaction 3A, we're essentially assuming that it's only going to add once. And then in our next reaction, we're actually going to take advantage of the fact that it does add more than once. I think I have a spot. Yeah. Let's see, I thought I had a slide here. Let's see, what did it look like? Okay. To write out the mechanism. So this is one of those examples. This is what it's starting with. But notice that there's 2 methyls attached at that alpha carbon. So the alpha carbon on the left doesn't have any hydrogen groups. So it's preventing the reaction from taking place on that carbon. And so we're going to start with the base in order to create the enolate. And so we've already seen this done under acidic conditions. So we're doing the exact same reaction under basic conditions now, but it has a lot less arrows and a lot less steps. So we're going to start by taking off that alpha hydrogen and creating a carbanion. So this is our keto to enolate taumerization step. And when we looked at our different enolate forms, this is one of them. And so we actually don't need to go any further than this for the enolate portion of the mechanism. So we only have one step left. We have our halogen, and I'm going to use bromine because that's what was in the example. But we're just going to do a nucleophilic attack. We're going to use that other bromine as a leaving group. And that's it. So it's just 2 steps. We're doing a proton transfer to create our enolate. So this is our enolate. And then we're doing a nucleophilic attack using that other bromine as a leaving group to create our product. So this mechanism is definitely less steps. And we saw that in our last chapter, that when things were under acidic conditions, there was usually more steps because there's hydrogens moving around. So acids mean proton transfers. So because we're under basic conditions, we don't need all of those proton transfers. Well, we can't do all those proton transfers because we're under basic conditions. All right, this was 3A, which means there is a 3B. So I mentioned that in this reaction, we're taking advantage of the fact that the bromine adds more than once. And so this one has very specific starting points. So this is 3B. we are starting with a methyl ketone. So we know what a ketone is. A methyl ketone means that one side is just a methyl group. So essentially it's exactly what it sounds like, or probably what you might guess it to be. And the first step here is reaction number 3A. We're reacting it with base and our bromine. This is what we're going to form. So this is the result of doing reaction number 3A 3 times. We're replacing all of the alpha hydrogens on that methyl group with a bromine. A CBr3, so a carbon with 3 bromines attached, is a good leaving group. So then we're going back to reactions from last chapter. We're using that base to do a nucleophilic attack at that carbonyl carbon. The pi bond becomes a lone pair. Here's our tetrahedral intermediate. That trihalogenated carbon is a good leaving group. So it takes off as a leaving group as we reform our carbonyl. And now we've created a carboxylic acid. So we're able to turn a ketone into a carboxylic acid. And so this is a really handy reaction because we talked about ketones in chapter 19, carboxylic acids in chapter 20. This is one of those rare reactions that allows us to kind of jump between functional group types. The last bullet point that's on here tells us that it works best if we don't have alpha hydrogens on the non-methyl group side. So notice for this one, it has that tert-butyl group. So our alpha carbon doesn't have any hydrogens attached to it. If there were hydrogens on the other side, those would just get replaced with bromines as well. It wouldn't turn into a leaving group because it wouldn't have 3 bromines on it. I'm assuming it would have like a chain or something. So if we had something like this, we would end up with our 3 bromines here and we would have 2 bromines here. And then honestly, it just becomes a mess and a nightmare and not something that we want to deal with or use. But that is what would happen if we had alpha hydrogens on both sides. So we're going to give this guy a star too. Forgot the star. So you do need to know the mechanism. This mechanism, if we were to draw out the full mechanism, we would have to do this 3 times to get all 3 bromines on there. And then follow it up with what's on the bottom of this screen. Questions about those reactions so far, about 1, 2, and 3? Okay, so reaction number 4. Reaction number 4 is an aldol addition reaction. So notice the title of this section. It's called aldol reactions. So we're going to look at aldol addition, aldol condensation, crossed aldol, intramolecular aldol, and that's kind of how a big chunk of this chapter goes. So after that, we do Claisen reactions, which are the same exact reaction, but instead of using aldehydes, we're going to use esters. And we're going to go through that same kind of listing. And so we end up with essentially groups of reactions. Our first group were halogenation, and then we have aldols, Claisens, and then the last group is kind of a mixture. When we start with our aldols, we start to make some bigger products. So this is number 4, aldol addition. Now, it is called an aldol because our product is going to have an aldehyde and an alcohol. So aldol, aldehyde, alcohol. It can actually work with a ketone as well, though. It's going to be messier because there's going to be more products. We'll look at that Wednesday, but it is possible. We tend to like to do them with aldehydes because it is going to be cleaner and we have less side products. Our only reactants base and water. And notice what base we're using for this. So I know we went through that whole few slides talking about hydrides and LDA, and we haven't even used them yet. In this case, we're using hydroxide because what we're going to do is we're going to turn our aldehyde into an enolate. Here's my enolate. But we're going to have that aldehyde react, or excuse me, we're going to have that enolate react with another aldehyde that's still in its aldehyde form. So we want to use that more moderate base so that we can have a mixture of the carbonyl form and the enolate form. So it is hydroxide on purpose. So let's talk mechanism. Here's our aldehyde. We're going to start with that proton transfer. So again, we're just removing that alpha hydrogen, creating a carbanion. We make our enolate. So we've done that kind of that first basic step that we're seeing in all these reactions. We're going to use that enolate as our nucleophile. So we're going to do a nucleophilic attack on the carbonyl carbon of the same aldehyde. So we are reacting two of these with each other. Because it's two of the same thing, we don't generally put a 2 in front of there, but if it helps you remember it, if it helps you see it, you can definitely do that. It's not wrong. Pi bond becomes a lone pair. So this is what we're creating. That oxygen has a negative charge. So the last step is just to do a protonation with the water there. So I'm going to do, let's see, I'm going to write this out up here with a little bit of color coding. Whoops. Forgot to switch colors. So you might see this already, and that's great. But if you don't, this might help you see the reaction that's happening. Okay. So the reaction that's occurring, or the new bond that's being formed, is this bond right here. We're going to form a new bond between the alpha carbon and the carbonyl carbon. So when it's labeled as a beta carbon in our product, the beta carbon is the former carbonyl carbon of our aldehyde. So we're forming a bond from here. I totally lied. Let's start those little ticks at the other spot. Here we go. We're gonna go from here to here. That's our new bond. We're going from alpha to carbonyl. I'm gonna draw this out for you. We're gonna do a practice problem, not on the next slide, but on the one after. We're gonna look at one more reaction that kind of gets paired up with this one a lot. So this one's called aldol addition. It attacks itself, but one needs to become a better yes, exactly. So one becomes a better nucleophile and then it attacks itself. Exactly. So this is aldol addition. This is aldol condensation. So number 5, giving it a star for the mechanism. Condensation, we think of water when we hear the word condensation. This is a type of dehydration reaction. So notice our starting material, we have our aldehyde. So again, aldehyde, I'm going to put or ketone in parentheses. We'll deal with the ketone thing later. We have base, we have water. The only difference between reaction number 4 and reaction number 5, heat. And what that heat is going to allow us to do is do a dehydration. So here is the product from reaction number 4. This is our aldol, our aldehyde alcohol. When that heat is in there, it's going to provide more energy. It's going to make those bonds easier to break. So we're going to do a proton transfer. We're going to steal that alpha hydrogen again, essentially making another enolate. And then we're going to use that carbanion to create a new pi bond, and our alcohol is a leaving group. Now we know that OHs aren't good leaving groups, but in this case it's going to work for two reasons. One, we're in basic conditions, so a negatively charged oxygen as a leaving group under basic conditions works, it makes sense, but also we have that heat, and so that heat is helping to break that bond and help that it's giving energy to help break that bond and make it easier to leave. So our final product then, this guy, is an alpha beta unsaturated aldehyde. So we are losing the OH group and the alpha hydrogen in order to create a double bond between the alpha and the beta carbons. Little stereo selectivity. The major product will be when the two larger groups are trans to each other. This is just alkene stability. So in this case, we do have two hydrogens attached, so we can say that the double bond is trans. But remember, cis and trans only work if we're comparing hydrogens. We have to compare two of the same thing. So when I say that the big groups are trans to each other, it's a little bit of a wiggle room on that definition. All right, so now that we have reaction number 4 and reaction number 5, we're going to look at an example / practice problem for this. And I'm going to show you a way to draw this out that hopefully will help you. The aldols have distinct odors. Well, aldehydes definitely do. I don't know if aldols do specifically. So we're going to draw this out in 2 steps. So I'm going to show you the aldol addition product. So this would be after the heat in the water, or excuse me, the base in the water. So this would be reaction number 4. And then we're going to add the heat. So this would be reaction number 5. You might see them separated like this. You might see it written all out as one step. On a test, it's pretty common to see them separated so that you can show me you know the difference between reaction 4 and 5. But either way. All right, so here is how I approach these. I'm just going to redraw this aldehyde. Now, let's try and line that up a little better. There we go. I know that the reaction is going to occur between the alpha carbon of one aldehyde and the carbonyl carbon of another. So I'm going to redraw or draw a new aldehyde, and I'm not going to line them up directly on top of each other. I'm just going to stagger them just a little bit. And then here is how I draw these products. I'm going to draw a new bond between the alpha. Oh, that was my elbow. I'm going to draw a new bond between the alpha carbon. I will, I promise. Oh, why won't you let me erase that line? Okay, we will use that line. From the alpha carbon to the carbonyl carbon, I'm going to erase that carbonyl and replace it with an alcohol. That is my aldol addition product. It's not pretty. It's not drawn in the way we would normally draw a structure. And you could count your carbons, kind of untwist it and draw it out as one long chain, and that's completely okay. But you can also just leave it in that form with bonds that are a little bit too long so that you can see the pieces of each of those aldehydes as they've come together to make this new aldol. Then, as we do the next step, as we do the heat, I'm going to draw in my hydrogen here. What we're going to remove is we're going to take off that alpha hydrogen. We're going to take off that OH group, and we're going to end up with a double, very wavy double bond, but we're going to end up with a double bond right there. So let's redraw this. And I don't think my stereochemistry is going to be right. So we might need to do a little bit of adjusting. But I'm going to have a double bond right here. And then we get that. Again, not the prettiest structure, but it does show us what we've created. And hopefully we can still see those two different molecules that have been coupled together. Now, I would say that this stereochemistry is not correct. When we look at our vicinal carbon, so when we look at this carbon right here, this side, this isobutyl group is obviously the bigger one. When we look at our other vicinal carbon, excuse me, I said vicinal, I meant vanillic, our other vanillic carbon, this isopropyl group is the bigger one. So right now our two large groups are cis to each other. So this would be my minor product. So to draw my major product, I'm going to keep the top half the exact same. There's my double bond. All I'm doing is I'm flipping these two groups around. How is an isopropyl bigger than an aldehyde? So, and it is a little bit of a judgment call here, but I will tell you. Let me draw this. There we go. So if we're looking at carbon, or we're looking at atom counts, they both have a carbon. So they're kind of tied at first. And remember, we're only talking about size here. There's a methyl here and a methyl here. This one just has a hydrogen though, so that's super tiny. And this one's just an oxygen. And an oxygen and a carbon are fairly similar in size. So because the isopropyl has the two carbon groups attached to it and our aldehyde only has one oxygen attached to it, that's how I made that judgment call. Let me erase my little circles here. Oh, I erased my oxygen. Would the oxygen, it wouldn't be counted twice because we're not like looking at like priorities like we would for R and S. We're not counting it to make sure that it's E or Z or anything. We're literally just looking at like how much size would each of these groups take up, because when we're deciding stereochemistry here, it's all about sterics and what would be bulkier. A way to see it better might be just to get rid of that alpha hydrogen or that aldehyde hydrogen. We don't show the other hydrogens usually. So even just taking off that aldehyde hydrogen makes the aldehyde side look smaller. Remember that hydrogen is super tiny. Yeah, just sterics. I'm gonna draw that back in though. So this would be our major based off of stereochemistry and sterics. Questions about either of those products? Okay. Before class on Wednesday, before we do lecture, if you don't quite see this yet, make sure that you spend some time looking at it, maybe spend some time doing a couple practice problems in that section, because where we're headed next is the same thing, but on speed. So we have to have that first reaction down in order to go the next step. The aldol one is kind of the basis for a lot of the other reactions we're going to be looking at. So take 20 minutes, 15 minutes to do some practice problems and look this one over before Wednesday, just to make sure that it makes sense and you got it down. Okay, I think we're at time, aren't we? Just about. So we are going to talk about the lab practical today. We're going to get on our other Zoom link though. So go ahead and log out, go click on the other Zoom link, and I will see you over there in just a couple minutes.